Okay, right. So before we get started, were there any questions on the homework that people wanted to have addressed before we went any further? Good? All right, let's go with it. All right, so I'll give you a sort of, where are we in the discussion? Today we're going to talk about maps between chain complexes. Helpfully named chain maps, or chain morphisms, depending on exactly the terminology you want to stick with. And what we want to do is we want to have these maps between chain complexes preserve the exactness structure, preserve the homology. So the idea is that with the appropriate constraints, maps between chain complexes ought to respect, and I'll be much more explicit about what I mean by respect, ought to respect homology. That's the main idea. So you want to have your maps between chain complexes do something that's appropriate with regards to homology. So in particular, if I have an exact sequence, it ought to preserve that exactness in some fashion. If I have a sequence that's got homology, it ought to do something to that homology that is reasonable. So it algebraically has to do that. Now, the way that this gets encoded in our discussion is it's actually very computational. So the insight is something called, well, you would perhaps call it commutativity, but it isn't exactly commutativity. But it is something called a commutative diagram. And so commutative diagrams make it very easy to capture at a high level what it means for this respect homology. And it's a really easy way to encode the property that turns out to be the right property. And commutative diagrams are the computational tool that are used throughout all of the computational topology. And in fact, more broadly in a branch of algebra called homological algebra. And even more broadly than that, something called category theory that is a very, very general foundational framework for mathematics. Okay, so I'm going to tell you today then, starting with commutative diagrams, what are they, how they can be used then to build these appropriate constraints for maps between chain complexes, and then we'll prove the theorem, but what does it mean to respect homology? Okay, and we'll have lots of examples. Okay, so what is a commutative diagram? Well, I guess I got to tell you what a diagram is in a precise sense. I mean, a diagram could be anything, really. Some picture I draw on the board. So a commutative diagram well, I'll say a commutative diagram of vector spaces. So I'll give you a definition. The commutative diagram of vector spaces is, well, it's a listing of vector spaces and linear maps among them, between some of them, or rather even more precisely between pairs of them. And it satisfies a certain property that composition of these linear maps is path independent. there are two sets of linear maps that get you from the same starting and ending point, or same starting and ending vector space, that if I form those two compositions of linear maps, then I end up with the same matrix. So, very simple kind of example, and these things are the sort of things that are really easy to screw up if you're not careful, so I brought some with me. I'm just going to find a nice small one here, because they can get, of course, heinously large. Okay. Here's one. So here's an example. So here's an R3. Here is an R5. Here is an R4, and here is an R3. And I'm going to label these maps. First I'm going to put them down as names. So I'll call this one M1, M2, M3, and M4. And this diagram, this is a diagram. Got a bunch of vector spaces and a bunch of linear maps. I've told you what the linear maps are, but I can certainly label them for you, and I have some matrices here to put down. This diagram commutes, or is a commutative diagram. This is a commutative diagram, or we just say this diagram commutes for short. When? Well, this is path independent. So this means if I start out, say, here, and I get to here, how many different ways can I get from here to here? One. So no constraint there. But if I go from here to here, how many different ways can I go from here to here? Two. I can go up and then over, or I can go over and then up. Those two different ways have to yield the same linear map compositions. So in particular, if I do M1 first and then M2, that's a composition. M2 compose M1. That's a linear map. That linear map has to be the same thing as doing M3 first and then M4. This composition. Now, the reason why we call this a commutative diagram is because if I label both of these as M2 and both of these as M1, of course that would work for the various sizes here. But then what would you see? It'd see M2 composed with M1 is equal to M1 composed with M2. And that's a statement of commutativity. But this is a generalization of that concept. So this is a generalization of the concept of commutativity. Okay, now I can sit down and write down matrices, and then you do matrix multiplication to verify that, yes, this does commute. These would have to be the same matrices. But it doesn't have to be a rectangle, it could be other shapes too. So let me give you another example of what this might look like. And there are lots of commutative diagrams. They're the bread and butter of algebraic topology. But the two typical types you see are these rectangles, like I just erased, and triangles, something like so. So I might have a vector space that can be very abstract. Here's a V, here's a W, and here's a, oops, this quotient, V quotient W. And in fact, you could have something like so. Here is a potentially commutative diagram. I need to, of course, label these with different names. This could be P, Q, and R. Now, the directions actually matter. These maps have directionality. This has a domain and a range. So this one commutes. If, well, how many paths do I have from V to V quotient W? Two paths. One of them is just Q, and the other one is R composed Q. Oops, R composed P, rather. Yeah, there we go. Now, actually, in this particular case, this is actually a very strong constraint. It's a very strong constraint. P and Q basically are projections, and R is also some kind of projection-like map. But if you look at it, it turns out this constraint is very strong. What does this tell you about R? Well, it really, R could be quite constrained in that it might be forced to be 0 depending on what this quotient is. If this quotient is 0, then R, what does R have to be? Forces R to be 0, potentially. And that, what does that do to Q? That also forces Q to 0. You can see that that shows up in this equation as well. Now, you get a different set of constraints if the maps go a little differently. So if instead I've got something that looks like, oh, I don't know, W, let me turn this first map around, maybe call it P tilde, go into V, and here's my R tilde going into V portion W, and here's my Q tilde. And see, this is an entirely different construction. Actually, wait, this one's more like Q tilde, isn't it? It's more like Q tilde, and this one's more like R tilde. It's a different set of equations for different maps. Now, if I wrote this one in this, one thing to realize though is I've drawn this and it looks basically like the same equation. Basically like the same equation, except the fact that the spaces are in different spots. So you could, this diagram is the same thing as this diagram over here. The position of the maps. So this is our Q tilde, but now this one has flipped around, and this one here is the R tilde. The position of where I draw the diagram does not matter. That's the point. It's just the organization of the maps. So depending on how you lay it out on the page, it's up to you. But the actual data that you laid down in terms of what the maps are and their compositions, that's what matters. Yeah?
This is reminding me of graph theory.
Ah, yeah.
Graphs are totally characterized by the set of vertices and edges.
Yeah. Yeah, you're absolutely right. In fact, what a diagram is it is a graph in that context that's been labeled in a very particular way. The vertices have been labeled with vector spaces, and the edges have been labeled with linear maps between them. Yes, that is a precise way to write this down. Although, don't necessarily need to think of it as a graph per se. But yeah, absolutely. This is exactly that sort of thing. So you can write down these kind of diagrams. Many different diagrams exist. And these maps, as a result, pick up constraints from the statement that the diagram commutes. Because then you get out an equation. See, in this case, we've got this equation. This different diagram yields a different set of equations. In particular, something like Q tilde composed of P tilde is going to equal R tilde. Different set of maps, different set of equations, but graphically it looks very similar. In fact, as far as the graphs are concerned, these are the same graphs. They've just got different labels. So the point is, this diagram here, different equation, but it's just a relating of that. So it's important to notice exactly how the thing is, which spaces are where and how they're linked. Okay, enough said on that. Let me actually show you that I'm not talking complete hot air, that these things actually exist. I'll give you an example of a commutative diagram. I'm going to put up the one that I had there a minute ago. And then I want to leverage this into discussing chain maps. All right. So I had this one here. I'm going to use a lot of room to draw this. So I have my R. This is an R5 here, an R3 here. This one is an R4. And this one is an, oops, this is R3, sorry. And this one is an R4. Okay. And I had maps like so. Okay. Now, I have to label these things with matrices. And the choice of matrices really matters. So let me put them down for you. This particular matrix, it's going from R5 to R3. So what shape is it? What shape is this map here? How many rows, how many columns?
5 columns, 3 rows.
5 columns, 3 rows. Yeah, 3 rows are the outputs, the columns are the input. So this is a 3 by 5 matrix. Here is a 3 by 5 matrix that I'd like to use. There's a 3 by 5 matrix on that particular map. Now, over here, it's a what shape? 3 by 4 matrix. Here's a 3 by 4 matrix. What about this one? This one is a 4 by 5 matrix. Here's the 4 by 5 matrix. Here's a 4 by 5 matrix. And I've got one more left, and it's a 3 by 3 matrix. And by the time let me just say this, I won't actually write this down, but by the time I've gotten this far, I know the shape of this matrix. It's a 3 by 3 matrix. I know an awful lot about what this matrix ought to do. Not completely specified, but an awful lot. In fact, it's kind of fun sometimes, write down these matrices, write down this much. See if you can reverse engineer what goes here. It's kind of like Sudoku, actually. Kind of like a game of Sudoku to try to fill that out. Now, in this particular case, I'll give you one that works. In fact, actually, Professor Casey at one point suggested that a good student computer science project would be a homological algebra Sudoku game.
I'm sure the computer science students here would really love that.
I'm sure they would. I haven't pursued this particular programming project. All right, so let's verify that this thing really is a commutative diagram. So what do we have to do? Well, we have to check that these matrix multiplications, these compositions, if I go this way or I go this way, it'll be the same thing. All right, so basically what we need to do is we need to do one of these multiplications first, and then try the other one, verify that they come out to be the same. So let's look at the top path. So what's the top path? Well, first I do this matrix. That matrix ends up on the left or right. Yeah, it's up on the right. And then this one ends up on the left. So the top path is this matrix multiplication. Row and column. Yeah, row and column. And 1, 0, 0, and a. All right, so there's the matrix multiplication. So we're going to go row into column a whole bunch of times. Row into column. That gives me this 0. Row into column. That gives me this 0 and one more. The next column, let me take this row into this first column, I get a -1. The second row into this column, I get a 1. The third row into this column, I get a 0. The next one is exactly the same. The next one, I pick up a first row into that column, gives me a -1, and then a 0, and then a row into column, a +1. And then the last one, I get row into column, I get 0, and -1, 1. Okay. Did I do that right? Good. Awesome. Likelihood of me doing linear algebra multiplications on board correctly, not very high. All right. Let's look at the bottom path. The bottom path is these two matrices. This one, then this one. in matrix multiplication order. Yeah, we good? I got another one, 0, -1, 0, 1, and a 0, 0, 1, 1. Okay. Now, before we do that, the multiplication, let's check the size. We've got the output of this is going to have 3 rows. 3 rows, check. How many columns? 1, 2, 3, 4, 5 columns. 5 columns, check. So it's got the right shape. If you don't have the right shape, immediately you know you don't have commutative diagram. Good thing to check. Okay, so now let's do out the multiplication. So this row into this column gives me a 0. This row, or rather the second row into this column, and this last one, they're both, the ones are falling in years, so those are both 0. This row into this column, I get a -1. This row into this column, I get these ones match up, and then this row into the column, I get a 0. Looking good so far. This row into this column, pick up the -1 there. This row into this column, pick up the 1, and now this into there, picking up the 0. This row into this column, picking up the -1. This row into this column, picking up, let's see, a 0. This row into this column, picking up a 1. Looking good thus far. All right, last one. This one to here, a 0, a -1, and a 1. So, yep, the same matrix. So, yes, this is a commutative diagram. So it's fairly straightforward to check if you've got a commutative diagram, just multiply it out. Even easier to do with a computer that knows about linear algebra, hence NumPy. You just do out those matrix multiplications and check to see if you have the same matrix. Important computational point, since we're using NumPy, which is using floating point arithmetic, do not check if the matrices are equal, because if there's a little bit of round off error, it won't be equal. Also, do not check to see if the difference is 0. Again, there might be a little bit of round off error. Check that the difference has a small absolute value. Okay, so that's what a commutative diagram is. Now, how do I turn that into a map between chain complexes, whatever that means? Okay, so let's sort of delve into that. And of course, commutative diagrams are how we're going to do this. And it'll be, like many things in algebraic topology, the moment you get the diagram on the board, it's clear what ought to happen. And then we can show why that's a useful thing for it to happen. Okay, so let's take 2 chain complexes. Let me say I've got a C and a D chain complex. So now let's consider 2 chain complexes. C and D. And by which I mean, let me expand this out. C with a bunch of maps, and I'll call these maps, I don't know, M's. Put a little dot to say that this is C1, 2, 3, 4, whatever, M1, 2, 3, 4, whatever. And here's the other guy, D's, with some maps as well. What should I call maps? N? Okay. Call them N's, then I'm right with that. All right. Okay, so I've got 2 chain complexes like that. A chain map between them. A chain map. Right. C to D is a, well, it is a commutative diagram of the form. And now I'm just going to write out the form. So I need to see my C chain complex and my D chain complex. Let me write that down. So for instance, I've got C2, maybe there's some stuff that came along for the ride, some C bigger ones. went down to C1, then C0, and then that's it. And these are the various M maps. There's an M2, an M1, and an M0. Similarly, I've got the D1 going on here. There's D2, here's D1, here's D0, and here's 0. Of course, this is N0, N1, and N2. Well, all of these things are vector spaces. Not thus far interesting as a commutative diagram. So what do? Well, looking at this, you'd probably say, well, all of these things are vector spaces. Vector spaces really want linear maps between them. I want to have a chain map going from here to here somehow. I got a bunch of vector spaces that kind of lined up nicely by index or by degree. Well, then just drop in a bunch of linear maps. Call them capital M2 here. Here's a capital M1. Here's a capital M0. And of course, probably more of them going that way.
Do they all necessarily have to be in the same direction?
And well, we want a chain map from the C1 to the D.
Okay.
So this is really taking me from the C to the D on this fashion. Yeah, you could build other diagrams that are more intricate, in which case they're not really chain maps in the same way. Okay, and this being a commutative diagram means what? Well, it means that a whole bunch of stuff, a whole bunch of constraint equations come into being. If I just consider this portion, that's just the square that we wrote down before. I've got one path this way and one path this way. It means if I do this little m1 first and the big m0, it's the same thing as doing big m1 then little n1. Of course, this part of the diagram looks exactly the same. And that says that this m2, little m2, followed by the big m1 is the same thing as big m2, followed by the little n2. And so on up the chain. Now what about, but I have other paths too. I've got multiple paths going from here to here, don't I? A whole bunch of them. A path like this, a path like this, and a path like that. 3 paths. Do I need to enumerate all of those equations though? No, I don't really need to, because the fact that this path and this path are equal is an immediate consequence of the fact that these 2 paths are equal. And then I popped this map on as the initial map. Once these 2 paths are the same, adding on another map to start doesn't change it.
So it's sufficient to just check the smaller.
That's right. So it's sufficient just to check all of the little squares. Okay. So you need to check a pair of equations for each square. Or, no, a pair of maps, single equation for each square. It's sufficient to check just each one of those squares. Because again, I either pre-compose with a map and then I've got that taken care of, or if I'm doing this one and this one, then I'm post-composing. Throwing this n after I've already established this first part is equal, then putting on n after the fact doesn't change it. Doesn't change the equality. Yeah.
So then in general with commutative diagrams, you only need to commute 2 transformations, and if you've gone through all the possible
It's a little more subtle than that.
Oh no?
It's a little more subtle than that. In fact, how's this for self-reference? There is a homology that tells you how much of that you need to compute. So we're building homology. We built homology for chain complexes. You can build a chain complex out of your commutative diagram and then use that chain complex to identify how much of the commutative diagram you need to check.
Okay. But in the case of this
It's a little too bad at the moment.
in the case of this particular one, you only need to check the corners.
Yeah, you need to check the small squares.
Right.
Yes. Check the small squares. Okay, so why is this a reasonable thing to do? And part of this becomes part of a habit. When you run across an algebraic topologist or homological algebraist or category theorist, if they draw a diagram on the board, they will be hoping, at the very least, that that diagram is commutative. Because commutativity gives rise to all sorts of nice properties. Without commutativity, all sorts of bad things happen. Now, The claim that I made at the beginning of this lecture was that if you start out using commutative diagrams, that was the key idea, then chain maps, so defined, do something nice to homology. That was my initial claim. So now we need to make good on that claim and show you how this construction does something nice to the respective homologies of the C chain complex and the D chain complex. In particular, if I take this chain map, it's going to do something appropriate to the homology. Now, homology is a vector space. It's a quotient vector space, but it's a vector space nevertheless. It should turn then into some kind of linear map amongst the homologies of these various chain complexes. And in fact, that's what happens. If you start out with this as a definition of a chain map, then in fact, that chain map is going to give rise to a whole bunch of linear maps amongst and between the homologies from this chain complex to this one. I'll write that down. And I also want to express a few other concepts about these chain maps before we go into the proof. Okay, so got this mental snapshot.
Hypothetically, if we had two exact chain complexes, one form a chain map, each individual mapping would also have to be exact. So if I went from C to D to D, that would still have to be exact.
Yeah, there are all sorts of important constraints that happen with chain maps amongst exact sequences.
Okay.
Absolutely. Yeah, and in fact, this becomes a very powerful reasoning methodology. Okay, so chain map, we named it Big M. That chain map, so now I'm going to turn this into a theorem. Chain map between these two chain complexes induces linear maps. And usually we write them with M with a little lower asterisk or a star. For every homology for the C guy, the D complex, they're all okay. And better yet, and by induces here, I now need to explain what that means. Certainly I can cook up linear maps, and I can say that they have something to do with chain map. But I mean something very specific. Such that important properties. First property is that if I take a chain map that really basically is built up of a whole bunch of identities, didn't change the chain complex at all, better not change the homologies. So, if all of the MI maps are identities, then M star, maybe I should label this with a K to carry out the fact that they could have different maps with different Ks. Second property is going to rely on something that I haven't proven yet, but will as a lemma towards proving this, is that if I have a composition of two chain maps, if I have a chain map, there's M, big M, three chain maps here, but three chain complexes, two chain maps, then when I compose their maps and form this special induced map, I could have done it in the other one. So in particular, if I go N compose N as chain maps, this is going to be a new chain map. I have to prove that. It is going to give me the same map as if I were to have done it individually. So in order to do this, I need to demonstrate to you, show to you that composition of chain maps is, again, another chain map. Because then this is some new chain map. I can find this induced map that I'm purporting exists. I'll show you how to compute that. And I'm asserting that that's going to be the same thing as if you had done it individually. Okay. Yeah.
What is K in this context?
K is remember when we compute the homology of a chain complex, you get a homology space for each spot in your chain complex. You get a boundary, or not a boundary, if you get a kernel of this map modulo the image of the map previous at this stage.
Mm-hmm.
Well, this stage can vary. That's the K.
So it would be something like for all K in the first n-1 integers?
Yes.
Okay.
Yeah, you could say that. Or you could just say all of them, yes. All of the integers. Extend by 0 if you so desire. Make it a really big chain complex.
Okay.
That without really losing any generality, you're just thinking about it. Okay, so in order to prove this theorem, and really to unpack its meaning, I need to do a bunch of things for you. First of all, I need to show you that this thing really makes sense as an identity, that I've got this composition, and that this composition makes some measure of sense. In fact, we really want to know that this composition is like a well-defined kind of thing. Like composition of functions, this is not a function. This chain map, it's a whole bunch of functions bundled together. I'm going to show that that does what you think it does in terms of composition. So first of all, I can compose them, and then the other useful property of this is that that composition is associative. If it isn't, it's kind of a malformed composition. Yeah?
So we're saying, you know that diagram that you just erased?
Yep.
Those M's are functions that map the homology of the C chain?
Yeah, these are, right, there's a lot of different levels of abstraction. I've got the M's without the star. The M's without the star are on the level of the chain complex. The M's with the star are on the homologies. So there's this interplay between the star ones and the not star ones. What were on the previous panel did not have stars. That was just the chain maps themselves. Does that answer your question?
And that those maps induce these maps?
That's right. Those maps somehow, and I'll tell you procedurally how they come about, those maps somehow give rise to this map. Or these maps, yes. Okay, so what I said a moment ago was that there is a distinction between the chain map itself, which is a bunch of linear maps amongst each of the various parts of the chain complex. There's a distinction between those and the maps with the star that are corresponding to the homology spaces. So there's that type distinction. Dave, you got a question?
Yeah, so I, in this case, am I.
Yep.
So that's saying.
I really should say for all I. Yeah.
Right, for all I.
Yeah.
It's saying if for all I, then this thing is true for all K.
Correct.
But if it's not true for even one I, it might be the case that all of the K's are non-identity.
It could be.
Okay.
It could. Well, in general, that's the logical implication. It won't happen. In fact, that does not occur. But
It won't happen, but according to this theorem, it could happen.
yes, I'm not intending to prove that stronger statement.
Sure.
Okay? All right, so we're clear on what we want to attempt to do. All right, so now let's just think about these chain maps. This is the goal. Let's think about just these chain maps. Think about composition and identities of chain maps. Because once we've got that construction, we understand how they work, then these induced maps become a little more clear. Okay, so let's go after that. I'll put that diagram that I had erased before, I'll put it back in some various forms. So, lemma. First of all, that there is an identity chain map. This is easy to prove. Basically what I'm saying is I'm saying if I map all the vertical arrows being identities, that's a chain map. The second thing that I want to show is that composition of chain maps is well defined. Since I've got this identity chain map kicking around, what I should have is I should have composition with the identity. Well, what should that do? Composition with the identity should do what?
Should give you the thing, like compose it with that.
Yeah, basically does nothing. Does nothing interesting. And the fourth thing is that composition is associative. Okay. So, the first one is easy. Let's prove this. The first one is easy. If I start out with my chain complex here, I want to make my identity chain map. Here's the same one. Each one of these is going to be an identity, putting ID for the identity map. And this is M2, M1, M0, M2, M1, M0. Well, do these squares commute? Yeah, because like composition with the identity on the level of functions does nothing. So notice MK composed with the identity is the same thing as the identity composed with MK for all K. Great. Composing with the identity does nothing on the level of functions, therefore this gives rise to this identity chain map. So choosing all identities gives you a chain map. Okay. Next thing, I want to show you that composition of chain maps is well defined. So I want to take two chain maps, that is 3 chain complexes, and map them along and show you that I end up with a chain map from the start to the finish. So this is point number 1. Point number 2, we'll keep the same chain complex here, and I'll just expand it. So here's my D2, my D1, my D0, my E2, my E1, and my E0. Now I have 2 chain maps, one going this way. Let's see, I think I had the big M first, and then the big N after that. Okay? Now I know that all the little squares commute, because both of these are chain maps. So what am I asking about then? Composition of chain maps is well defined. Well, I should be able to go from C2 directly to E2 without ever going through D2. So really what I'm focusing on then, when I try to compose these chain maps, is I want to go from the top to the bottom row, top to the bottom row, top to the bottom row directly. How am I going to do that?
Just define like PI equal to NI after MI.
Exactly. Basically the idea is you go this way. And why do I know that this rectangle here is a commutative diagram? Going from here to here is the same thing as going from here to here.
Because for the first sort of step, we have that lowercase m1 and capital M0 is is capital M1, N1.
That's right. So essentially what we do is we break it up into 2 steps. I know this part of the diagram commutes, so I can precompose it with this one. That says that this path is the same thing as this path. Then I take the second step and I realize that this path is the same thing as this path. Therefore, they're all equal. So 3 steps. The first one, first you do this path is the same as this path. And the way that we had done before, diagrams just turn 90 degrees. Basically, we're precomposing with this one. That's a commutative square. And then we showed that this zigzag path is the same thing as this path. But since then, this is equal to this is equal to that, therefore that's equal to that. Okay, so that establishes point number 2. So we've got an identity, we've got this composition of chain maps as well defined. Now we can take care of this third one very easily by imagining if I put identities here, well, then that didn't really do it. This portion of the diagram didn't do anything at all. So when I go from here to here, and then to here, well, I didn't really do anything when I went from here to here, and same thing on this stage and every stage. So that takes care of the third statement. Okay. Now, fourth one, unfortunately, diagrammatic mathematics ends up taking up huge amounts of board space. And associativity requires, yes, another chain map. I'm not going to write out the 4th chain map up here or down below. Why is this true at a high level? What is this going to follow from?
Well, the sensitivity of composition of these sort of linear functions.
Yeah, associativity of linear maps or associativity of functions. But composition of, for chain maps being associative, comes right about from the composition of functions. Basically, you're doing this same kind of process. I'm really forming a map from C to D to, and then D to E, and then E to F. Well, that really is, I can take them, I can group them in any order to get from C all the way to F. And it doesn't matter one bit. I come up with the same. And that's the reason for you. So I'm not going to write that down for the diagrams page. And it's not as worth it as some other such big diagrammatic computations one can do. So, okay. So that establishes then, I'm going to put quotes around that. I didn't actually write it out, but it's true by explanation, verbally true anyway. So what does this do? Well, this tells me that chain maps and their composition play with chain complexes kind of like functions. Functions are kind of like the sets, and the chain maps are kind of like the functions on them, in much the same way that vector spaces are kind of like the spaces and the linear maps are like the functions. In much the same way that sets and functions play together, in much the same way that groups and homomorphisms play. And this seems really, really like I'm saying the same thing over and over again. Of course, I'm doing that on purpose. This particular analogy is something that plays an important role. And in fact, these axioms here can be summarized, once you know it, by the following statement, that chain maps, the chain complexes, and chain maps form a category. And the axioms of what it means to be a category is just these statements as I've written them. You just swap out chain map and chain complex everywhere you see it. So for instance, with functions, there is an identity function on sets. Composition of functions is well defined. Composition with the identity function gives you back the function you started with. And composition of functions is associative. So sets with functions also forms a category. There are lots and lots of other categories. This observation led to the development of something called category theory, and algebraic topology had a really big part because of this computational aspect. Okay. Now, what this means is this means that chain maps are somehow structure preserving in the right way. And that's what that theorem that we want to now prove is saying for us. It's saying that what these chain maps are doing is they're doing something very useful on the level of homology. So now let me tell you how this works. Okay. So, let's put up our two chain complexes we have. Here's our first chain complex, and here's our second chain complex. What we're going to do is we're going to focus our attention right on the middle one, the degree 1 stage in our diagram. So let's focus our attention there. Degree 1 stage. And I'm going to write in my chain block. So I'm going to focus our attention right there, right on the D1 stage. Let's suppose that I have an element of the kernel of this map. This map here, I think we agreed that these here were m's, little m's. Let's suppose I have an element of the kernel of M1. So suppose I have an element, let's call it X. Let me grab the yellow. Well, yellow's not very good color. Let's say I've got an X. And that if I map this through M, I get to 0. So M1 of X is 0. That really doesn't look like 0. Map it by M1, and I get to 0. What does that tell me about the image of X through big M1? See, I've got an X here, it mapped over to 0 here. It also mapped up over to something over here, didn't it? Well, this doesn't have to be 0.
We know N1 composed with M1.
Yeah, that's what we know. So we know that this thing here, over here, let's call this Y. This is M1 of X. It's certainly an element here. I don't know if it's non-zero or not. But I do know
It's in the kernel of N1.
But I do know it's in the kernel of M1. That's exactly right, because of the commutativity. So the equation in question here is that M0 after M1 is the same thing as N1 after M1. And so let's take a look at, let's see here, M0 of M1 of X, that's N1 of M1 of X. That's what the equation says. Now the left side of this equation, though, we're saying M1 of 0 is 0. And big M0 is linear. So this is big M0 of 0, but we know that is 0 because M0, big M0 is linear. And I'm calling this guy here Y, contents of this. So this is saying that M1 of Y is 0. Put another way, what does this chain map do? It takes the kernel of each and every one of these spaces in the chain complex into the kernel over here. So it preserves kernels. So the commutativity is really useful in that regard. It's preserving kernels. So what does it do to images? What is it doing to images? Well, it should basically do the same kind of thing, but like reverse in some fashion. Okay. Everyone got this down? I'm going to erase the annotations. What's that?
Should we be writing this as a theorem?
I already did, actually. I'm now proving it, in fact.
Okay.
But I'm not being as explicit about stating that, but this is exactly the proof of that.
Gotcha.
I'm actually building that induced map for you, piece by piece. I'll make that clear.
Okay.
Okay, so let me erase my annotations. Erase my annotations. So I've got my X here, and I want it to be in the image of M2. So what does that mean? What do I know the fact that this is in the image of M2? So purely that means there is an element over here. Maybe call it Z or something. Z is going to map over to X. X is in the image of M2, so there is a Z. There exists a Z that's going to map to it through M2. Okay? Well, that Z also maps to something down here. Z maps down to something over here. We'll call this guy Y. Okay? Well, what happens to Y?
Y must get mapped to capital M1 X.
Yeah, Y through N2 gets mapped to something. And that something is what? Well, it's none other than what this thing got mapped to. This thing here is M1 of X. Oh, so what that says is this takes something that's in the image of M2 to something that is indeed manifestly in the image of M2. So chain maps preserve kernels and they preserve images. If I've got something in the kernel here, it stays in the kernel down here. If I've got something in the image, it stays in the image. So maybe rather than stating it as a theorem, this is somewhat of a lemma, and I'll state it as such. So that if C mapped to D through M is a chain map, and these are my chain complexes. If I've got a chain map, and then what's true? Well, we know that now that M, K, of kernel of little mk is contained inside the kernel of nk and mk of the image of the previous map, m image of mk plus 1, is in the image of mk. That's what we've proven. Take anything in the kernel, it stays in the kernel. Take anything in the image, it stays in the image. So chain complexes do something really useful then, because in particular now, we know something about these. They're doing something very important for us. They're telling something, they're telling us that when I have this chain map going on, it's going to do something to the numerator and the denominator, so to speak, of this quotient that is homology. The homology is the kernel modulo of the image, the kernel modulo of the image. Well, this is getting preserved by the chain map, as is this. And that, in a nutshell, is what the induced map does for homology. It takes both of these together. So now I need to tell you how that works. Okay. All right. Let's let that sit for a moment while I now erase this diagram. And then go back and state the part of the theorem for the homology. And then actually those other various properties we want to prove about the composition fall right out of this. These in particular, what happens if I have two chain maps so I compose them? Well, the kernel is just going to stay inside the kernel the whole way down. The image is going to stay in the image the whole way down. That's basically what you need. All right, so now what does this do to homology? Put it another way, how do we define this M star K? Which, remember, what this is going to do is this is going to take HK of C and turn it into an HK of B. Okay, now how does that work? Well, remember what this thing is. This thing is the kernel of MK, quotient the image, MK plus 1. And I want this to get mapped into the kernel of NK, quotient the image of NK plus 1. This is the type of this map. It has the type of mapping between these spaces. Okay, well, we know for a fact that what's going on here, so we know from our lemma. I'm just going to rewrite the lemma. This statement here, and the construction we did in order to prove it, says that this MK map really is a map like this. Every element of the kernel of the first guy got mapped into the kernel of the second one. So this is just a restatement of that lemma. And let me also restate as a function the same thing for the image. So both of these are well-defined linear maps. So both okay. Now, what I want to do then is I want to think about what's this telling me on the level of this quotient. I'm taking, what do these quotient elements look like? They're cosets. Remember, they're cosets. They're an element of the kernel plus this entire image. Element of the kernel gets mapped to some other element of the kernel. This entire image gets mapped somewhere else inside this entire image. So in fact, then all we're doing, and here's this map in fact does just that. So that's actually what the definition then of this induced map is doing. So we literally can write that down. Now let's do that. So here we go. M star, okay, of an element here. So what is this going to be? This is going to be some element of the kernel. Call it D or X. We were calling it X. That's totally fine. Image of MK plus 1. This X, we're assuming that's in the kernel of MK. And so what is this thing? Well, it's a linear map, isn't it? So by linearity, this thing is going to be M star K, or just MK, really. M works on this, takes my kernel to my kernel, so I'll just call it MK. In fact, I'm going to define it like this. MK on that, still in the kernel, plus MK of the image of MK plus 1. Well, this thing here is not the entire image. But there's really no harm, if I'm pushing it over here, there's really no harm in just crossing this whole thing out and saying image of MK plus 1. Just making that coset a little bigger, making that particular representative in here picked out. That's literally the definition of that. That's it. So this is the right map. Now you ask, what about the other properties that I stated? If I have the identity map, why does the identity chain map turn into the identity maps here? What does it do? Well, it doesn't do anything here at all. It gives me just back X. Does it do anything here? No, not at all. So the identity map, the identity chain map turns into the identity induced map on homology. What about composition? Well, gosh, composition is just really going to amount to, forgetting about this for the moment, and just doing composition over here. This will get bigger potentially. Fine, whatever. Doesn't bother me any. It'll end up the same is the point, regardless. It does not matter how I'm performing my compositions. Over here, this is just composition of functions. We already proved that diagram in unit. So we're good. And that's it. That's the proof that I did. Now you might ask, gosh, how do you compute this? How in heck do you write down this kind of map? Well, it's generally speaking a real pain. Which is in fact why, generally speaking, you want software to do that. That's actually the content of the projects, is to start writing down these induced maps. So I think the last problem in the first project is to compute these induced maps on chain complexes. And how do you do that? The realization is that when you go kernel modulo image, that you're doing a projection. So in essence, now let me diagram this thing out. I've completed the proof. Let me just show you what this looks like from the diagram I've seen. And this explains, from a matrix standpoint, what you've got to do. So here's my kernel of mk getting mapped to my kernel of my nk. This is mk. Now here's my quotient, my homology of C. Here's my other quotient, my homology of D. What we've ended up doing is we built this map here. Okay. Now, when I go from here to here, what have I done? Well, I've gone from taking elements of this kernel to elements plus this image, big image floating around. Essentially, I've went from elements to cosets. When I do that quotient, that essentially amounts to a projection. So there's a projection here. This is a projection. And this too is a projection. So the point of the matter is both of them, I mean, this is say, projection C and this is projection D. They're potentially quite different projections. So if you want to find this map, well, what do you have access to from a software standpoint?
All the MKs.
All the MKs and these projection matrices. So in fact, that's nearly everything you need to find in order to write down the MKs. Now, you look at this and you say, well, wait a moment. I want to go from here to here. I want this. I've got this map and I've got this map, but this map, really, if I wanted to form this map as a composition, to this thing that we needed a diagram, I really want to go this way. I really want to go around the diagram this way because then it would be this composed with this, composed with that. That would give me this map. And in software, that's exactly what you want. What goes on here? What do I do here for this projection?
Well, can the projection be inverted?
Projections are not injective, generally.
Right.
So it's surjective, yes, but injective, no. Can't invert it exactly, but you know what? What's the problem? Every point has at least one preimage. And the problem is that every point has lots of preimages. It turns out, actually, if I'm only interested in this composition, whatever choice I've made over here is going to come out in the wash when I do it over here. So it doesn't matter. Pick some inversion. Some inversion will go back this way. Find some pre-images. The great thing about this is this can be done very easily linear algebraically. This is a linear solution. Least squares linear solve will do that, i.e. just reduce the thing. This guy here we could write down explicitly because we know what all the chain maps are. And this projection here is just basically computing the homology of this chain complex. So it really basically amounts to just forming this composition of these three matrices. And you're good.
In some ways, you're voting for the projection C just by restricting the domain.
Yeah, that's exactly right. You're restricting the domain, and then you're good to go. And in fact, in software, it literally turns out to be this product of three matrices. Yeah.
So the projection, what it's actually doing is when you apply the projection matrix to a space, what you're doing is you're actually applying it to the bases.
Yeah. Yeah, you can think of it that way because then it is all matrices, exactly.
Is that the way that the projection should be defined, or is that just?
I don't know. Should is perhaps a pedagogical point. It certainly works that way.
Okay.
Yeah.
We're just looking at the irreducible representation.
Of course. Yes. Although I'm trying to be a little bit more pedestrian. But yes. Other questions? Okay. Well, then that ends what I wanted to present. And we're a little bit behind schedule due to the snow, so what I want to do next time we meet, i.e. 1 week from today, is give you some examples of these sort of things, walk through them, and in particular look at certain classes of chain maps that yield identity maps here that themselves are not identity. To show you that, there's this homology is telling you strictly less information than chain.